Delaware Tech, Chemistry 100, Chemistry 110, Unit 3 continued, History of the Atom. People have been thinking about the atom for literally about 2,400 years now. And it is thought that the first person who actually thought about anything conceptually like an atom was the ancient Greek Democritus. Democritus lived around 400 BC, and there was another person associated with Democritus, Lycopus. Lycopus is sometimes referred to as Democritus's teacher, but a lot of people think Lycopus never actually existed and was just written about for literary purposes. But Democritus actually proposed that everything was made of these substances, these individual particles that couldn't be divided anymore, that he called atomos. And atomos is derived from two Greek words, and I'll write them up here to show you the parts. The first one is just the letter A, and the other was tomos. And this was actually with the Greek alphabet, but I'm going to write this with the Roman alphabet, the one that we know and love. And the word A means without or not. And tomos means to cut or cuttable. You know tome in a couple words. Anatomy. Anatomy literally means cut oneself. Microtome means small cutter. It's scalpels. Okay? So atomos literally means can't be cut or indivisible. And what Democritus thought was that he was looking at sand in Greece where he lived, and he noticed that the big chunks of sand were made of small particles of sand, and they were made of smaller pieces of sand, and he envisioned that if he went small enough, eventually he would get to some microscopic piece that still looked just like sand, but couldn't be broken up into any smaller particles. So they were indivisible, they all looked the same, they might have been different shapes for different kinds of particles, so he thought that stone was all made of microscopic little stone particles, and fur was made of microscopic little hair particles that were all identical to the other hair particles, and the stone particles were all identical to the other stone particles, but they actually looked like small versions of the other, and they were just simple particles that couldn't be broken down anymore, and there was no internal structure in them. And that's what Democritus thought, and that's actually a pretty good start for what an atom is. However, Aristotle, who was this very famous philosopher and what we call a polymath. A polymath means they're really good at a lot of different topics. And Aristotle was ridiculously brilliant in a lot of different fields, including early biology. He was the first one who did systematic analysis of biology. He looked at anatomy of human beings and other organisms. He looked at philosophy. He looked at physics. He looked at government and economy. But one of the things he looked at was the structure of everything around him, what we now call the chemistry of everything around us. And he decided in his head that everything was made of combinations of air, fire, earth, and water, and a fifth element that he had called ether or aether, A-E-T-H-E-R, and he believed this was a magical heavenly force that held everything together. And Empedocles, who lived a little bit later than him, took Aristotle's work and said, okay, we're going to disregard the ether part, but we're still going to keep Aristotle's four elements. And unfortunately, this was the prevailing thought for hundreds of years, actually about 2,000 years, until about the 1600s in the Age of Enlightenment, when people were starting to do actual scientific method to learn things. And one of the great early chemists, who's considered the father of chemistry, his name is not on here, it appears in a later slide, was a man named Antoine Lavoisier. And Lavoisier really started developing the first systematic methods of chemistry. And Dalton read about him, John Dalton read about him. He was a teacher, and he did some of his own work with studying gases. And he came up with a set of 5 rules that actually hold up extremely well even today about the nature of atoms and how they are put together to form matter. So we now refer to that as Dalton's atomic theory of matter. It was first published in 1808, and I'll show you that in a second. Now, at this point, Dalton still believed that each particle, these atoms, they were just solid balls, essentially, with no internal structure. And J.J. Thomson was the first person to actually look and discover things within the structure of an atom. And what J.J. Thomson discovered was the electron, the negatively charged particles that are a component of the atom. And he envisioned that the atom was this ball, but it was essentially a sea of uniform positive charge spread throughout, and the negative charges, the electrons, were little beads that appeared in that uniform background of positive charge. And he referred to this as the plum pudding model, or this became known as the plum pudding model, because plum pudding is an English dessert that has certain pieces of sweet food embedded in the sweet cake of the quote-unquote plum pudding. We would more modernly think of this as the chocolate chip model. And so this was the prevailing model of what the atom looked like for about 10 years or so. And then Rutherford, who was this incredibly sharp physicist and chemist who lived in the late 1800s, early 1900s, Rutherford knew of J.J. Thomson's work, and he wanted to test it. And Rutherford had already won the Nobel Prize for discovering something called the alpha particle, which is part of radioactivity, which we won't discuss in Chem 100. It is discussed in Chem 110. And he decided to use these particles that he knew were positively charged and a little heavier than individual particles like a proton. In fact, it was about 4 times heavier and had twice the positive charge. And what he did was he bombarded something, and it was gold foil, and we'll talk about this in detail in a couple slides here, but he bombarded this piece of gold foil, this sheet of gold, and he wanted to see how the atom would respond to this bombardment of these positively charged particles. And I'll show you the results, but what he discovered was that it couldn't possibly be the plum pudding model. That model had to be incorrect. The atom couldn't be this uniform sea of positive charge with little beads of negative charge throughout. He decided that the positive charge was actually concentrated in the center of the atom in a very, very tiny spot in the middle. In other words, it didn't take up much space, and that's where all the positive charge was of the atom, and that the electrons were around it. So a very different model. And this became known as the Rutherford model, and then that was modified by a man named Niels Bohr, a brilliant Danish physicist. So I'll go into that in a couple slides as well. So Dalton's theory, he had 5 postulates of his theory, and these 5 hold up remarkably well, as I mentioned already. Let me erase that for just a second. Okay, so first he said that all matter is made of tiny indivisible particles called atoms. Okay, he got that straight from Democritus. And we know that that's more or less true, except if we use nuclear chemistry, we can even break the atoms up into protons, neutrons, and electrons, or even smaller atoms. He also said that atoms of the same element are identical, while those of different elements are different. Well, this is mostly correct, except we now know about isotopes that I mentioned earlier. In other words, all atoms of hydrogen are not exactly the same. They all have 1 proton. That's what makes them hydrogen. All helium has 2 protons. That's what makes them helium. All carbon has 6 protons. That's what makes it carbon. But they may have differing numbers of neutrons, and therefore there might be different isotopes within the same element. Within hydrogen, I mentioned there's hydrogen 1, 2, and 3. Within carbon, we have carbon 12, but we also have carbon 13 and carbon 14. And people have even made carbon down to, I believe, carbon 8 or 9, all the way up to at least carbon 20, I think. So we're always making new isotopes, but they're man-made isotopes. The third postulate of Dalton's atomic theory is that atoms of different elements combine in whole number ratios to form compounds. And a lot of this work was started by Antoine Lavoisier, the French scientist I mentioned earlier, but Dalton continued it, and what he showed was that if you look at any individual compound, say H2O, there's a ratio of 2 hydrogen atoms for every 1 atom of oxygen. or CO2, carbon dioxide. There's a ratio of 1 carbon to every 2 oxygens, and different compounds have different ratios of different elements. He also said that chemical reactions involve the rearrangement of atoms. In other words, you're not destroying atoms, you're not creating atoms out of thin air, you're just rearranging what they're attached to. An atom may be attached to 1 other atom or 3 other atoms, and then after a chemical reaction happens, it's attached to something completely different. So it's just rearranging what's attached to what. And then number 5, atoms cannot be created, subdivided, or destroyed, and this also is directly from Antoine Lavoisier, as well as some of Dalton's own discoveries and thoughts. And this is mostly correct, again, except for nuclear reactions, which can do all kinds of damage to atoms themselves. So Antoine Lavoisier, I only mention him because he's considered the father of modern chemistry. He lived in the late 1700s. Unfortunately, after his incredibly amazing contributions to chemistry, he was also a great humanitarian. He tried to revolutionize how prisoners were treated in prisons. He tried to improve lighting on the streets of Paris, France. In the 1700s, he improved the water purity and sanitation there. He was a great humanitarian, even though he came from an incredibly wealthy background, and he tried to do good for people. And one of the things he tried to do good for was to keep people from being cheated by people that were selling tobacco, who were soaking the tobacco in too much water to make it feel heavier, so that they would try to scam the people that were buying it. Well, when the French Revolution happened, the tobacco sellers, who were annoyed with Antoine Lavoisier for preventing them from cheating customers, basically accused him of cheating customers. So there were a lot of false accusations. That wasn't the only one. And Lavoisier, unfortunately, was found guilty by a court of Napoleon's revolution, French Revolution, and he was put to death by having his head cut off by the guillotine in 1794. About a year and a half later, they admitted that it was a complete travesty of justice and that he was killed for no good reason. But unfortunately, his death was incredibly tragic. And a great mathematician, a famous mathematician named Lagrange, said it only took them an instant to cut off that head, but France may never produce another like it for a century. And that really is true. He was just irreplaceable. His wife, who was also an amazing chemist of her own right, trained formally after meeting Lavoisier, and her name Marie-Anne Lavoisier, and she actually took it upon herself to publish his works after he was dead. So we know about this work that he did, and this is part of the reason why Dalton was able to come up with these rules. So Rutherford, Ernest Rutherford, an amazing physicist and chemist, who actually was credited with a lot of discoveries, including the alpha particle. He believed J.J. Thomson's plum pudding model when he first heard it. Everybody did. It was as good a model as anybody had for the structure of the atom. J.J. Thomson had already shown that there were electrons in the atom. So he wanted to see if that was true. So like any good scientist, you design a testable hypothesis, and the testable hypothesis was J.J. Thomson's plum pudding model. So Rutherford designed an experiment to test that hypothesis. So he wanted to use these radioactive particles, these alpha particles from uranium that he had discovered, and he wanted to shoot them at gold. Gold was something easy to hammer flat, because he wanted to make it as flat as possible so there'd be as few atoms in a single layer as possible. So this incredibly thin piece of gold, it was about 1,000 atoms thick, which is actually incredibly thin. It sounds like a lot of atoms, but that is a ridiculously small number when we're talking about atoms. And he shot it at it. So when the atoms would go through the gold, they would hit this fluorescent screen that was behind the gold foil. So he had this chunk of uranium inside a lead block in a tube, so that the alpha particles that the uranium was releasing in all directions would only go out the tube. And they would hit the gold foil, and if he presumed they would all go through the gold, because of the plum pudding model suggested that these positively charged alpha particles would just go through this uniform sea of positive charge without being deflected. So he thought that they just go through the charge the charged particles, the particles that had both positive and negative charges in it, this sea of positive with little dots of negative. He thought they would just scream on through and hit that fluorescent screen and light up, and he'd see all the particles hitting on the other side. So this is what he expected. He expected to shoot this beam through and everything would come through and hit the fluorescent screen in one spot, and that would be it. That's if the plum pudding model was correct. However, that's not what he saw. What he saw was this. He saw that most of it did go straight on through. The vast majority went straight on through. But a significant number of the alpha particles were deflected, sometimes a little bit, sometimes almost backwards. And that told him something. He didn't know exactly what it was right away. It actually took him a couple years of analysis to really understand what happened. But what he decided was that most of the space of the atom was empty. Now, we now know that's not quite true. Most of the space of the atom is filled with the electron cloud, but the electron cloud is not very dense, so it really is incapable of stopping these heavy alpha particles piercing through it. So, because some of the particles were deflected, he realized that the positive charge of an atom must not be evenly distributed. It must be concentrated in one spot, presumably the center of the atom, and it was very heavy and concentrated, and he called that the nucleus of the atom. The nucleus, the word nucleus means little nut. In fact, the word nut and the word nucleus come from the same word in Latin, nux. And so he thought it was this intensely concentrated kernel, this tiny nut in the center of the atom, this nucleus, where the positive charge was all concentrated, and that most of the alpha particles would just go right through, but some of them, if they got near the nucleus, would be bounced back or bounced to the side. They would be deflected because positive charges repel other positive charges. Likes repel likes when it comes to charges. And so he saw this, and that made him realize that it was a totally different model with the nucleus in the center with all the positive charge. Now, Niels Bohr worked with Rutherford. Niels Bohr was a Danish physicist who made some corrections in his model because his model really didn't count for where the electrons were. So just a couple years later, Rutherford proposed his model in 1911. 2 years later, after working with Rutherford, Bohr came up with his model that was a variation of this. He said, okay, the atom still has that nucleus where all the positive charges are in the center. That's okay. But the electrons, they must be in orbits around the nucleus, and sort of like planets buzzing around the sun in our solar system, and that they occupy these rings that are moving around. The electrons are moving around in rings, in orbits around the nucleus, and that there are no in-between rings. In other words, you had to be in the first ring or the second ring or the third ring, but you couldn't be between those rings. And each ring corresponded to different energy. The ones near the nucleus were lower energy. The ones farther away from the nucleus were higher energy. And so he decided there were all these different levels, what we now refer to as shells, but we don't use that term anymore because it was soon realized that even this model needed to be fixed. They knew there were problems with this model, and his model said that there were all these different orbits, and by the way, his model didn't say the orbits were all in the same plane. So some of the orbits are tilted one way, some of the orbits are tilted another, but the electrons are all buzzing around the nucleus that has the protons in it. We now know it also has the neutrons. They didn't know about the neutrons themselves just then. But they knew the mass was there, they knew the protons were there, and they assumed the electrons were just buzzing around in these different orbits. And then it was realized later by a couple more physicists and a lot of other physicists working in conjunction that it was much more complicated than this. The nucleus was right, but where the electrons were was probably much more complicated. Well, it turned out that modern structure that was much more complicated was first devised by a man named Erwin Erwin Schrodinger, a Austrian-Irish physicist, and this was further along developed by a man named Werner Heisenberg from Germany. Both of these physicists essentially revolutionized our understanding of the atom, and they kept the information from Rutherford and Bohr, but refined where the electrons actually were and how they were behaving in the atom. So the nucleus, as I mentioned already, has the vast majority of the mass of the atom, because protons and neutrons have a lot more mass than electrons. And that's all right in that center dot that's in the middle of the atom. So most of the mass is in this tiny little space in the atom. But the electrons, that's a different story. The electrons occupy this cloud, this volume of space that surrounds the nucleus, and the bulk of the volume of the atom is actually this electron cloud, where the electrons are. And while you might hear people say, oh, most of the atom is empty space, that's one way to look at it, but the fact is that's not true. The volume of the atom is mostly composed of this electron cloud, and you can say, well, where is the electron in that cloud? Well, the cloud is the electron. Mathematicians and physicists like to say that the cloud is a probability function, a mathematical function, and that function is the electron. It's not a particle the way we think about here's a ball here and here's a ball here. It's a cloud. It's a diffuse volume of space where the electron is. Now, we'll still think of the electrons as being dots in some instances, but in reality, it really behaves like a smearing out of the whole volume of space. So the bottom line here is that the nucleus has the protons and neutrons where most of the mass is, and the electron cloud has the vast majority of the volume, but very little mass of the atom. So, and it's not really empty space. So, a little chart here to remind you of the differences between the three particles that make up the atom: the proton, neutron, and electron. They're symbolized as P, N, and E, sometimes with their charges, plus 0 and -1, respectively. And so the charge of a proton is +1, the charge of an electron is -1, and a neutron is neutral, 0 charge. The first two particles are the heavier particles, and they're both in the nucleus. The proton and neutron make up the protons, and the neutrons make up the nucleus. The electrons make up the electron cloud and has very little mass. And it turns out the protons and neutrons are about the same mass. The neutron's just slightly heavier than the proton, but we're gonna call each of them a relative mass of about 1. We'll call it an atomic mass unit. We now call these Daltons, named after John Dalton, who came up with those rules we mentioned in the last module. So 1 Dalton, or 1 atomic mass unit, or simply 1 unit, as is sometimes referred to nowadays. But the electrons don't hold units. So this is why if you want a rough idea of how heavy an atom is, you just count up how many protons and neutrons are in the nucleus, and that gives you a ballpark idea of how many atomic mass units that particular atom has. It's not exact because neither the proton nor the neutron is exactly 1, but it's a close enough count for the purposes of looking at relative mass. So atoms are very small. Even with that electron cloud on it, the atoms are incredibly tiny. They're a trillionth of a meter in diameter, in units of trillions of meters, of trillionths of meters in diameter. The helium nucleus is the smallest, the helium atom is the smallest of all the atoms. It's 32 picometers radius. That means it's 64 picometers wide, or 64 trillionths of a meter in diameter. A francium atom is almost 10 times wider, which means it's 10 times taller, 10 times deeper, 10 times wider, or 1,000 times bigger in terms of the whole volume. So atoms range in size by about 1,000-fold from the smallest to the largest atoms. They're all still incredibly tiny, but there is a big difference in size between different atoms. The nucleus within the atom is incredibly tiny inside the atom. If an atom was the size of a stadium, of a giant football stadium, the nucleus would be about the size of a marble, to give you a point of reference. The radius of a nucleus is about 10 to the minus 15 meters. So that's 1,000 times smaller in radius, 100 to 1,000 times smaller in radius than the whole atom. So the nucleus is about a billionth of the volume of the atom. So that's even smaller. The density of the atom is, will vary with the atom, but the density of the nucleus is insanely high. 10 to the 14 grams per mil. Remember, water is 1 gram per mil. This is 1 followed by 14 zeros. If you had a substance made of pure nucleus of atoms without the electron clouds, and they were just nuclei crammed against each other, 1 mil, 1 centimeter cubed, 1 cc, would weigh about the same as 2,600 aircraft carriers. If you've ever heard of neutron stars are essentially a giant star made of a single atomic nucleus. All the particles have been crushed into one giant collection of neutrons, like a big neutral nucleus of an atom. And so neutron stars are ridiculously dense. And with that, we'll leave it here, and we'll come back to atomic number and mass number next time.